And then Q&A. Okay, take it away, Brian.
All right, great. Yeah, so this is lecture 4, and we're going to talk, kind of put some pieces together, talk about what I've called vaguely information dynamics, expanding on the topic we talked about at the end of last time. Here are some references again. All the previous 3 notes are now on the Slack, and I'll post this one either later today or tomorrow. And yeah, we'll also make some analogies to black holes, and we'll talk about some current directions in the field at the end. So let me start with a recap. What we talked about last time was this membrane picture of entanglement dynamics. And in particular, we had a picture of a circuit, which I kept drawing as this empty box. But as we discussed, you should think of this box as being filled with microscopic unitaries, sort of the building blocks of time evolution. So I'm just, rather than trying to draw that a million times over, I'm just coarse graining into this blank thing, but just remember it's there. And we said if you want to say compute like the entropy of this region with X, what you do is draw some kind of curve, which is characterized by a velocity, and the entanglement of X at time t would be equal to the minimum over the curve of S equilibrium integral dt this y intention plus possibly a t equals 0 contribution. Right. And that was the picture, and we saw that this picture recovered kind of our expectations for entanglement growth. In the case where there's no initial entanglement, or in the case where there's partial initial entanglement, it could capture saturation of entanglement in a nice way. And we also saw how this picture was very precisely true for random circuits. And the big idea of last time was that this picture, suitably coarse-grained, could capture the entanglement dynamics of a broad class of systems. So now I want to talk a little bit more about information spreading. This is the topic that we were discussing at the end of last time. And the idea here again is I have my circuit and I put information in here, and I want to get information out up there. And in particular, I want to ask the question, what's the smallest region that contains the information? So if this were information encoded in the electromagnetic field, then you know, just look at the speed of light. That defines the region size as a function of time, and whatever information you put into the electromagnetic field is certainly contained in that region at that time, right? Because that's the basic speed limit that limits the motion of light. But in this context, where we have potentially some strongly interacting dynamics or some quantum chaotic system, light's not particularly chaotic because it doesn't interact with itself. At least it's not many-body chaotic. We saw that the answer to this question can be different. So in the case where there's no initial entanglement, it turns out that the the size of the region that you need to recover the information grows not at the speed of light, which is not even really defined for this model, and not at the butterfly speed or the maximum speed, but actually at this entanglement speed, dE, which was the growth rate at time 0. So last time, no initial entanglement. The information velocity VI was equal to VE. And this information velocity you can think of as being defined as size of region equals VIT. Size of that region. Okay, so now I want to repeat the calculation, but for the case where we have arbitrary initial entanglement. Right? And the way that we track the information in our relationship was to look at, instead of putting information in, we just entangle the system with a reference, and we track where the entanglement of that reference is located in the system. So we'll do the same thing here. Track information flow by tracking entanglement with a reference. Which I call R. So here's the picture. Let's put our information in with our reference R. Let's consider a region here, which starts on the left side and goes out to distance X. And as we've, and let's say down here, we have some kind of entangled initial state. This is in addition to the entanglement with the reference. S of X t equals 0 is something like S naught X. And S naught can be anything from 0 up to S equilibrium, the maximum value. Okay, and as we've seen several times now, there's sort of two candidate surfaces or candidate curves. One of them looks like this. Suppose we want to compute the entropy of AX, which is this region up here. Well, one of them is a sort of saturation-like curve, which goes like this at VB. And notice that this curve excludes R, right? So I don't have to have any extra cost to cut off R from AX. And the other curve is one that has a lower slope. This is V star of S naught, which is argmin so this is the minimizer. This is the velocity that you would have when you have initial entanglement slope S naught. And in this case, if you're computing the entropy of A, well, you have to also cut off R from A because R is not part of A. So you have an extra piece to your surface down there. Right. So the red surface, and of course, let me just remind you that also there's a contribution from this part because of the initial state. And so there's basically two situations here, right? If the red surface dominates, then the entropy is equal to S equilibrium X, right? It's just saturated. If the blue surface dominates, it's T S equilibrium epsilon of V star. And this little +1 here is from the R part. And now you can repeat the calculation for AXR, and then the entropy for R itself is always just 1 in units of log Q or in units of log 2, depending on whether we're doing qubits or Q level systems or whatever. So we have similar calculation for SAXR. And then S of R is always equal to 1. Again, normalized for qubits, say. So 1 would mean just one bell pair or 1 unit of entanglement. So then we have the following conclusion. If the entropy of AX is saturated, then the mutual information between AX and R is equal to 0. And if the entropy of AX has not saturated, then the mutual information is 2. So in other words, if you look at a region that's big enough, so its entropy is still changing in time, then it is highly entangled with the reference. And so it contains the information that you put into that first law. But if the region is too small at a given moment in time, so that entropy is no longer changing, then it's no longer entangled with the reference. And it no longer contains access. It no longer contains the information that you put in. That information is contained elsewhere in other degrees of freedom in the system. And what's nice about this picture is that it makes that sort of viscerally obvious, because it either the minimal membrane or minimal line sort of includes R in principle, or it doesn't. And that's the simple test. Of course, you go through all the calculation and you get exactly what I said, but pictorially it also is easy to see just by asking whether the dominant curve includes R or not.
Hi, Brian.
Yeah.
Maybe a naive question, but if you insert the information at the bottom and you say before the saturation you have that information basically all in R because the mutual information is 2, but then later on after it's saturated, then you don't have that information at all in R. But I would expect like the information to be maybe more spread out throughout the circuit, but to still have part of that information in in that AEX region. So why it is not?
Yeah, this is like a sort of I would say a sort of deep thing actually, is that there really is like a phase transition almost, where once AX is too small at a given moment in time, it just looks totally thermalized or totally equilibrated, and it has no memory of what the initial state of the system was. So this is a general property of chaotic evolution, that you forget your initial conditions effectively. Of course, the system's evolution is unitary, so in principle, the information is encoded in some subtle way in the system. But in practice, you can't learn where you came from by looking at small sets of degrees of freedom. And this is giving a very precise sort of information theoretic quantification of that, where we see that once the entropy is saturated to its equilibrium value, then there's sort of no room for information about the initial state.
So does it mean basically that whatever, in principle, whatever size of region AX you get, you cannot recover the information about the initial state unless you have full control over the whole state? Is that the idea?
Well, so in this case, like if the entropy of AX is saturated, you just can't recover. You can't recover the information at all. Period. If the entropy of AX is not saturated, you in principle can, but it can be very complicated. That's a question of complexity or sort of computational difficulty versus information theoretic possibility. And that's interesting subject, but not what I'm claiming anything about here. What's sort of counterintuitive and weird, but a property of this thing is that, suppose AX can't reconstruct the information, but there's a slightly bigger region, AX plus delta X, whose entropy is not yet saturated, that can reconstruct it, right? Then the mutual information of AX with R and the mutual information of delta AX with R are both separately zero. But the mutual information of the combined object with R can be large. So this is the sort of fundamental weirdness you have to get your head around, that there's, the parts can know very little or nothing about something that the whole is entangled with.
It's maybe a stretch to see it this way, but does it have, in some sense, to do with entanglement wedge reconstruction, this whole picture? Because it seems like if you take two small regions on the boundary, then you can reconstruct only up to a certain point in the bulk. But if you take both of those regions, your entanglement wedge is larger than the sum of the two previous entanglement wedges. So it seems like it's a similar picture, right?
That's right, yeah. I would say, I will try to draw an analogy in a little bit of that type, but I would say that the reason why both of these things are possible is because of this feature of quantum states that, part one can know nothing about your information, part two can know nothing about, but part one plus part two can know something about it. And the reason is because you can do these much more complex entangled operations on the two things combined that you can't do on each of them by themselves separately. I unfortunately don't have time to really go into this, but the concept of a quantum error correcting code is another way of thinking about this same kind of thing. That's a situation where, the code can correct a certain number of errors, say, which means, roughly speaking, that you can lose parts of the system and still have the information encoded, right? So no single part has the information, but collectively they have the information. And that's the same kind of thing that's happening here.
Thanks.
Okay, so because of this, we just need to know the saturation time. And you can compute that easily enough by just comparing when these two things, when the two options here are the same. That sets the saturation time for a given region of size X. And what this implies is that the information velocity in this case is just equal to that minimizer. And it also has an alternate expression in terms of the rate divided by 1 minus S over S equilibrium. So I emphasize, I'm not showing you the algebraic details here, but this just follows, it's just a calculation that follows from what we said before. Okay. So I encourage you to work this out if you're interested, but it just follows by computing the saturation time and saying that the minimal size region is the region that's just about to saturate its entropy. And so that determines the speed. Okay. Now let me show you how this works. So here is a figure from, I forget who the first author of that was. Yes. Ouch. From the paper that we wrote, where we compare these various things. So what we're doing here is looking at, so this is an Ising chain, same kind of Hamiltonian as we had before. Like this with some parameters, which you can look up in the paper. We're looking at the information velocity on the y-axis, sorry, versus this quantity, which I call F, that's the entanglement fraction, which in our notation here is just equal to S naught over S equilibrium. So it's just the fraction you are towards maximally entangled or towards equilibrium entangled. This red line at the top is the butterfly speed, which I claimed is the same as Vmax. This blue line here is that V star quantity. So what we have different notation. We called VE the rate gamma because we allowed it to depend on the fraction F. So this blue curve is V star of S naught, right? And the black curve is VI. And how do we measure these things? So butterfly speed you can get by calculating out of time order correlators. So that's one separate independent measurement. Secondly, you can get V star by just computing the entanglement rate, starting with a partially entangled state and just letting the system evolve, again, using exact diagonalization and seeing what the rate is. So that's the second independent measurement. We compute the entanglement growth rate as a function of initial entanglement slope. And then the third independent measurement is we do this thing where we actually literally entangle with a reference and we track the mutual information with different sized regions with that reference as a function of time. And we define a contour of, reconstructability or knowledge as the place where the mutual information is 1. So the maximum value is 2, no correlation is 0, so we just pick 1. We can check that it doesn't depend too much on that choice. And we track the contours of that mutual information equals 1 in space-time. And those look like, again, straight lines asymptotically, and that defines the information speed VI. And so the point of this plot is that the information speed VI and the independently measured entangling speed V star, or what goes into V star, actually just approximately agree at small values of the fraction. There starts to be a little bit of deviation as you go higher up, and then something more deviant is happening at the largest scale. But we have good evidence to say that this behavior up here is coming just from finite size effect. The basic issue is that the entanglement growth rate is very small when you're nearly maximally entangled already. So in this region where you're already close to fully entangled, the growth rate is very small, and it's just very hard to measure that appreciably with, say, 14 spins or 20 spins. It's just hard to see it. Right? So the data is noisy up here, so we don't necessarily think that there's anything wrong with the underlying theory. It's just the system is too small to clearly see it. But down here in the region where we do have good data, where we're not dividing two small numbers by each other, we have almost perfect agreement, and then, you know, agreement within, say, you know, 10% or so elsewhere. So in other words, the sort of, you know, very simple membrane picture that we discussed on the previous slide can actually quantitatively predict relations between these three independently measured quantities. And in particular, you sort of see that, you know, again, within this sort of 10%, you know, problem with the data, that this butterfly speed, which we call Vmax, is roughly setting the largest possible speed in the system. So you never get an observed information velocity bigger than that. The prediction of the theory is that asymptotically the information velocity would just be equal to VB when the entanglement fraction is close to 1. Okay. So I'm happy to answer questions about what we did in detail, but the takeaway here is just that that theory that we've been developing now for more than for like 2 lectures, it works, and it quantitatively relates non-trivial quantities in a strongly interacting quantum many-body system, in this case a spin chain, and we also showed that it works for ADS-CFT. Specifically, what we considered were charged black holes created via various quenches. This was nice because it allowed us to dial the entanglement speed and the butterfly speed independently of each other, so we could explore a wide range of parameters. And we verified this formula was true in that case. Okay, so it predicts entanglement growth rates correctly. It predicts saturation. It also gives you these highly non-trivial relationships between different speeds that you can measure. And so actually, it really quantifies precisely the dynamics of information, how information spreads in your quantum many-body system as a function of time. Okay, let's talk next about the scrambled state. So here the idea is the following. Let's just imagine we have a system and we've evolved it for a long time. Right? So we have a finite size system. We've evolved it for a time that's much longer than the system is wide. Right? And now if we look at a, say, small subsystem, what we would expect is the information, the minimal membrane looks like this, where the slope is VB. And we know that this then gives you the prediction that the entropy of that small subsystem is just thermal. Right? Then there's a corresponding complementary large subsystem. Its minimal membrane is actually the same as the case for the small subsystem, because they have the same entropy. And the important point here is that no matter where this small subsystem is located in the overall system, I've drawn it here at the left edge, but I could put it at the right edge, or I could put it in the middle. No matter where I put it, its entropy is saturated. And this is a statement that all the small subsystems look thermal at late time, right? In fact, what this predicts is that everything essentially up to half the total system will look thermal. Now, by analogy with ADS-CFT and entanglement wedge reconstruction, which I believe you've learned about now, you might think that, roughly speaking, this region of the circuit is something that the small subsystem knows about, whereas this region of the circuit is the region, the part of the circuit that the large subsystem knows about. Right? And again, I want to emphasize that it doesn't mean that the nature of the circuit deep in the past is easily discernible from the state in the future. It could be encoded in a very complicated way. Actually, I saw that at the end of Netta's lecture, she was talking about Python's lunch. So that's relevant here because this is like a constriction. So we do have a conjecture that the community has conjectured that, you know, it actually is quite hard to recover what's in the deep past in this case. And for some kinds of models, one can prove that, but mostly it's a conjecture. But in any event, it seems like the information should in principle be encoded there. And now I want to make an analogy to a black hole. Which looks like the following. You can see that if I look at this circuit, the small size region never penetrates into the circuit farther than a certain point. So roughly speaking, there's like a line here we can draw. Which is, I would say, roughly analogous to a horizon. In the following sense, in ADS-CFT, if you form a black hole from collapse, but you look at the entropy of small subsystems at late time, those entropies are computed from HRT surfaces that remain outside the horizon. And they probe the exterior geometry only. In fact, they're just the equilibrium RT surface at late time. So in this analogy, we can sort of say if the surfaces, if these minimal lines don't penetrate past a certain point in the network, we could call that roughly like a horizon. So that means this part here, which is inside the horizon or behind the horizon, should be regarded as roughly analogous to the interior. And this actually kind of makes sense because, again, in the context of ADS-CFT, the interior of the black hole grows with time in a certain sense. And this has been interpreted, starting with the work of Susskind and building on that with many people, including myself. This growth of the interior has been interpreted as a growth of circuit complexity. So in ADS-CFT, the growth of the interior is conjectured to be related to growth and complexity. And here, what does complexity means? It means just the number of gates it requires to make this state. But that's exactly what's going on here. The volume, the space-time volume of this region is just the size of the system times the time it evolved for. So it's roughly like the number of gates you need to prepare that quantum state.
Can I ask a question here?
Yeah, please.
So you're saying that the analogy is with collapsed black holes at late times where the HRT surface is outside the horizon.
Yeah.
But it seems like in that case, your entanglement wedge is actually only outside the horizon, while in this case, it's like your entanglement wedge is behind the horizon, but if you are behind the horizon, then the reconstruction is like highly complex. So is this more similar to the picture where you have actually an HRT surface outside, or it's more similar to what Neda was talking about at the end, like Python's launch, where you have this minimal extremal surface, and then the minimal extremal surface deep inside the horizon, and whatever is in the middle of the two surfaces is hard to reconstruct, but in principle possible?
Yeah, good question. So I would say, I'll say a couple of things. I think it is still consistent with the entanglement wedge picture, because the idea would be like, in an old black hole, but a black hole formed by collapse, you look at a small subsystem and its entanglement, its HRT surface stays outside and just hugs the horizons there, does something, right? So then the HRT surface of the complement is the same thing. And by purity, it just includes all the interior as well, right? So the HRT surface does not go inside, but because it's, because you have to push the homology surface through the actual black hole to get to the edge, you have to assume that actually you can push it through the interior so it actually has access to the inside. Otherwise, it wouldn't be the right surface. So the HRT surface is the same in both cases, as as happens, but the interpretation of the correctable region is different in the two cases, or the recoverable region. So I think that's true, but also I think this Python's lunch story and something like that also in principle, well, I don't know if it applies here, but a similar kind of complexity phenomenon probably is taking place here. Or at least I would say the evidence we have for that claim is as strong in these random circuits or in Hamiltonian spin chains as it is in ADS-CFT.
So, sorry, so what you meant is that the small subsystem corresponds to the small subsystem whose entanglement wedge is all in the outside, and the large subsystems corresponds to the complementary region.
That's right. That's right.
Okay. Now it's clear. Thank you.
Okay, so there is an analogy here, and you can even take it further in the sense that if you imagine the small subsystem is the evaporated part of the black hole. So I could make a more elaborate model where I couple this system to some bath, and I can let energy flow into the bath. A very simplified toy version of that is to imagine that you take your system and you just remove pieces of it one at a time. You remove qubits and you take them somewhere else. That's the radiation. and then the dynamics can continue on whatever remains. And what you can convince yourself is that there is actually a transition, a phase transition within this minimal membrane model, where once you've removed enough of the entropy, once the system has radiated too much, so to speak, then suddenly there's a phase transition, and now the radiation is what has access to the interior instead of the black hole. And that's essentially what's happening at a very coarse level when you have an entanglement island. So I would say at this stage, what we understand, I mean, what I'm telling you is really, I would say, kind of the frontiers in this area. But from certain course point of view, most of the ingredients of the information problem, in some sense, have avatars or analogs in even something as simple as a spin chain. And the same kinds of phase transition phenomena are visible in this membrane effective picture. And I personally think it's interesting to, explore in more detail that correspondence and try to make, more sense of what's going on. Okay, so we got about 30 minutes left. I want to talk about a couple of extensions and then talk about the frontiers, and that'll wrap up. Right? So I want to talk about, in addition to states, talk about operators, because entanglement of operators is an important topic. And I want to first talk about the case where the operator is just an evolution operator itself, U. Now, what does operator entanglement mean? It roughly means the following thing. It means that you take U and you apply it to a system of bell pairs, say defined on the left and a right. And you think of U as being something which acts on the right, on the left, sorry, and does nothing to the right. So the picture is like this. You have U, which is an operator, and you apply it to a bell pair. And this defines a quantum state on two copies whose expansion in a certain basis contains all the information about that operator. So pictorially, what you're doing is you're bending the input leg around and making an output. And this is called the state operator mapping. And it's very useful because it just lets us think of operators which have two legs. And so technically are members of a vector space, which is maps from the vector space to itself, which is isomorphic to V tensor, V dagger, the conjugate, or the dual is the technical term. And so this is just representing the operator as a vector in the vector space times the dual space, which is isomorphic to the space of operators. And so now we can choose qubits on the left, and we can choose qubits on the right. And so now the picture would look something like this. We still have U, but now we have, say, let's call this X left. I guess I transposed it here, sorry about that, but hopefully it's not too confusing. So we consider a bunch of qubits on the left from, say, the boundary up to position x left, and we consider a bunch of qubits on the right from the boundary up to the position x right. So our region now has degrees of freedom on both sides, on the left and the right. Which again, from this picture is like having degrees of freedom in the future and in the past. So hopefully the analogy is clear. Sorry. And so we have the same kind of problem, except now the membrane has two fixed points. It has to do something like this. Oh, sorry. Plus, we can allow horizontal segments. So let's say for simplicity, we're looking at x left equals x right. Then at time 0, there's no entanglement. And the minimal surface in this case is obviously just this. And indeed, when they're collapsed together, when the time is 0, this curve has no length. And so there's no entanglement. Now, that sounds funny, right? The left is entangled with the right, but here we're including the left and the right together, right? So they're entangled amongst themselves, but not with the rest of the chain. And that's what this is telling us. Then, as usual, there's also another possibility, for example, this possibility, which would correspond to saturation. And so saying if you look at this pair of complementary regions on two sides of your operator state, that first entropy will grow and then eventually it saturates once you have this red curve dominating. And that's again a calculation that you can do in ADS-CFT, for example, and you'll see exactly the same behavior. This was first discussed in a paper of Hartman and Moldesena some years ago, but it's just the same kind of structure. And of course, you can work out what happens if you vary x left and x right, and you get an interesting and intricate structure. Okay, so now I want to talk about growing operators. Which is, say, W of t equals u w u dagger. And this is a local operator. So this is the context in which people think about butterfly effect, out of time order correlators, etc. And what's the picture of this thing? Well, you have something like this. You have your local operator W, and you have U dagger. But there's an effective light cone. Like this. Because if U and U dagger, if W was not present, then U and U dagger would just cancel TV's identity. Right. And so parts of the circuit or parts of the evolution, which are outside its effective light cone, do cancel. And the part which is in the future and the past of the light cone fail to cancel. And that's the picture of the growing operator. So that means we can cancel this way. So those cancel out. And what we're left with is a picture like this. Where in this region it's the identity. And in here it's a non-trivial, basically it's like part of U and part of U diagram. And again, the expectation is that the slope here is V max, which is also, in cases we understand, the same as the butterfly speed. So any questions about the setup there, the picture? There are several non-trivial sort of heuristic assumptions that like the region that we can cut out is exactly the butterfly speed, etc. That's something you'd like in principle to prove or to understand more deeply. But here we'll take it as just an assumption and see what it gives us. So if I take my growing operator and suppose I want to, let's say this hourglass. So I want to compute the entropy of a region X, which is defined to be all of these dashed lines with X measured from the center. So just as before, if X were equal to a minus number, which is half the width of this cone, then the entropy would be 0. When X is equal to 0, we have a picture like this. And you would expect the minimal curve to just do that. But if X is greater than 0, then you have a picture like this. Suppose X is here. Well, what's the minimal curve now? Well, a little bit of thought will show you that it looks something like this. The reason being that it can get kind of a shortcut by passing through this identity region, because in the identity region, nothing happens. So we should add an extra rule that in the identity region, the membrane tension is 0. So it costs no length or membrane energy for the curve to go through this region because it's just identity, right? So the circuit's not changing any entanglement. You're not having to cut any bonds. So if we zoom in, on just the top, And we have our curve, which hits there. Let's call this distance delta t. Obviously, the total time here is t. And we'll let the speed here be v. You do a little bit of geometry, and you figure out that, okay, the slope of the black line is VB. So VB times t minus delta t. That's this point here. We start at 0. We go out in the x direction by VBT, but only for a time t minus delta t, because we stop at this time step. And that had better be equal to x plus v delta t. And what this tells us is that delta t vbt minus x over vb plus v. So just a little bit of geometry to figure out what delta t is as a function of this velocity v. And then we're saying that the entropy is equal to the minimum over delta t, or equivalently over v, of 2 t, 2 delta t s equilibrium epsilon v. Why the 2? This is from the upper and lower regions, right? We had the curve in both. Based on our previous slide, this is min over v. To S equilibrium. We use our formula for delta t. And then VBT minus x doesn't depend on delta t or v at all. Those are just parameters of the circuit. So what you get is something here. Equals to what they call in the Jonet et al. Paper spread entropy density. But this quantity is just this min of E over V plus VB. Right. You remember from saturation story that what we were doing there is minimizing over V, E over V, epsilon over V. Now we're minimizing epsilon over V plus VB. So you get a different minimum. And it actually predicts something non-trivial, even though the time evolution operator, even though the growing operator is built from 2 copies of U and U dagger, its entropy is actually growing at a slower rate because it has this cancellation from the light plume structure. So you get a non-trivial quantitative prediction, and you can again check this with a spin chain, and that's one of the results in the Jonet et al. Paper that I listed on the first slide. I won't show you the actual picture, but it compares reasonably well. I I want to make one final comment, which is about higher dimensions. You can, of course, imagine many elaborations on the basic story, but the simplest extension is to think now not about a square, but about a cube. Like that. And we can have, say, a region here, A, and then we would look for some kind of minimal membrane that ends on A. Maybe I shouldn't draw it as a straight line because it's not a straight line in general. So let me put a little bit of curvature into it. And with no initial entanglement, or let's say what I want to do is let me change this picture a little bit, because that's actually the picture for saturation. So let me draw the picture like this. Right, you have some kind of membrane which can, as in the 1D case, hit the initial state. And then with no initial entanglement. S of A at T is equal to the min over this blue thing of S equilibrium integral over dt integral over some additional parameter dl epsilon of the velocity, right? So think of L as like something like this. And so I just want to make the point that now, even in so now in higher dimensions, the generic surface is going to be curved. And the reason is because you have a cost associated with the spatial extent of the membrane. And so now it can pay for the membrane to have a velocity because it can reduce its spatial extent in the past. And so this means higher dimensions is much more complicated. So if you want to look at the entanglement of a sphere, for example, at time 0, its growth rate is equal to the membrane tension at 0 velocity. But as time passes, you get a more complicated function that probes the whole tension, or at least part of it. However, for strips, you get a quasi 1D result again. Okay, so it's just interesting and more complicated in higher dimensions, and there's even more richness. So in the final couple of minutes, I just want to mention one frontier. There's a lot of things one can do. So first of all, you can try to imagine extending this model to all kinds of other situations. For example, you can consider all-to-all interactions or power law interactions or models defined on graphs. You can try to include conservation laws, how a conservation law is coupled to this sort of hydrodynamics of entanglement. Those are all interesting questions. You can also try, for example, to make this analogy with HRT surfaces and Ryuta-Hinagi more precise. And with entanglement with reconstruction, with black hole information problem, etc. One thing I want to mention here, though, is a new subject. Which goes by the name of measurement induced phase transition. So here's the idea. We add quantum measurements to the unitary circuit. And what this means is really a quantum measurement in the sense that, say you have a qubit, you take this qubit, you measure it in, say, the computational basis. If you get 0, then that qubit is now in state 0 and you proceed with the circuit. And if you get 1, that qubit is now in the state 1 and you proceed with the circuit. So it's not coupling to the environment and forgetting about what you measure. You're keeping the record. The record is something that you know and maintain. And then going forward, it's like the, what do they call it, collapse, right? You have 0 or 1, depending on what you got for your measurement outcome. Pictorially, you can represent it like this. Suppose you have a qubit running its own business, and you measure it. You get some outcome, and you can think of that outcome as something where the incoming qubit is projected onto a state. The probability is related to the amplitude, and then it's output again in that same state, right? So you just come in, you project your incoming state onto that measurement basis, the different amplitudes of the probabilities, or the square of the amplitudes of the probabilities, and then what comes out at the top is just the product state. And then that can get plugged into the circuit and you can have further evolution. So the picture is that you would have your circuit, and now you would modify it by lots of little random inclusions where you're breaking lines. And you can imagine with enough inclusions, you lose entanglement. Because you see these inclusions have the property that the minimal surface can pass through them for no cost, because you've broken a bond, right? Which is a pictorial way of saying you made a measurement and you get a random outcome, which is a product state. And so now it doesn't cost anything to pass through that bond. So if you have a measurement rate or a measurement probability, per unit time. So you suppose you, at every step of time, you measure each qubit independently with some probability p. Then you get a phase diagram for long times. Not too long, but that's a gloss over that. Whereas a function of p at 1 and at 0, you have a critical value, PC, and here it's highly entangled. meaning volume law. And here, it's lightly entangled. So this is area law. This is volume law. So this is a novel kind of quantum phase transition that takes place essentially at infinite temperature or for kind of highly excited states between a situation where you have a lot of entanglement at late time, like our thermalized state, or where you have very little entanglement at late time. So basically it's a question of whether these holes in your network are such that the typical surface can pass through them without a lot of cost or not. So you might think it's related to percolation, for example, and indeed there is a connection. And I should have put some references here, but I didn't, so I'll add the references when I upload them. But this is a recent subject that was first discussed just a few years ago and is now capturing a lot of attention in the condensed matter and quantum information communities. And again, it seems to be related to black hole, various black hole type things. There are similar kinds of phenomena that happen there, but the connections are still early days. So I thought I would just mention this as a really new topic that's something you might want to think about going forward. And with that, thanks for listening, and I'll wrap up there.
Wonderful. Thanks very much. All right. Questions for Brian?
I had a question.
Mm-hmm.
So is it possible to understand using your membrane picture, the page curve?
Yeah, I mean, you get something sort of similar where, if I go back to this picture, where was it? Yeah, if you go to this picture and you think that I take away the small subsystem is what I call the radiation, say. So I just keep adding more and more to the radiation until eventually the small system is actually the big subsystem, right? It has more than half the degrees of freedom. And then what will happen is that the surface will now go like this. And the radiation will have access to the interior, and the radiation's entropy will get small again because it's related to the entropy of the remaining small black hole. And again, I want to caution that this large and small is just in terms of information, not in terms of like physical size or energy. So, you know, in a full model, you have lots of notions of big and small, or lots of ways to compare. Here, it's sort of a purely information theoretic comparison. But that's the essence of the page curve result. So you also have a page curve for spin chains, if you like. It's just maybe less mysterious.
So I mean, in page curve, I think the initial growth goes linearly, and then after the page time, the curve sort of curves. You know, it's not a line anymore. Is it possible to see from here? Why is that?
Yeah, I would say, if I understand what you're talking about correctly, I would say that's something that's not so clear how to see. Like, this is a very coarse picture. I mean, as you saw, it still makes a lot of very concrete predictions. But in terms of calculating, like, say, the saturation, for example, which we saw from the numerical data had some non-trivial time dependence, that's like maybe less easy to see here, or it's not clear how precisely to trust this membrane picture when you're asking about those finer scale details. Okay, so the short answer is I'm not sure. It's possible if you know, suitably flesh out the picture, that it can give you a sensible result for like that kind of like saturation dynamics, like the approach to saturation, or the crossover as you get near maximal entanglement. But at this level that I've outlined here, I don't think it sees that in a very clear way.
So you also mentioned that when one crosses the page time, the membrane changes its direction and sort of sees the interior of the black hole. I didn't understand, why does it see the interior of the black hole? Because I mean the horizon is along that gray dashed line, right? So the membrane can still stay above it instead of going in.
Right, but yeah, the membrane can stay above, but the region of the circuit that I associate with that region depends on what side of the membrane it's on. Right, so like once the large subsystem is like the radiation, then the membrane is like as drawn here, but now I interpret the whole shaded red region as the part of the circuit that the large subsystem can have access to.
And this picture, it doesn't necessarily only apply to black holes in ADS, right? Because I can think of any black hole in any kind of space-time should sort of, roughly can be described by this picture. I mean, I guess I have to specify what do I mean by the small subsystem and large subsystem for a long time. So that's where I think ADS CFT becomes helpful. But
yeah,
is it possible to, think about this in other contexts?
Let me put it this way. I would encourage you to try. So, it's not clear what difficulties you will encounter, and they may require some serious thought or maybe some obstacles, but I think the tools are there, and it's worth seeing how far one can push them. Because certainly from a sort of many-body physics point of view, like spin chains of various types or whatever, this picture looks quite general, and it doesn't seem like I need, it seems to apply even for like what you might call a system with a very stringy gravity dual, like a Ising model where you perturb weakly with some integrability breaking term or something like that, or just the 2+1 Ising model, right, which is a chaotic, at least medium interacting conformal field theory in a certain regime. And this picture, I guess, would roughly apply to that. I mean, no one's ever checked that. It's hard to calculate, but that's the conjecture. And yeah, so it seems like you should be able to make sense of these notions.
Did you also mention the reference where this picture can be found?
No, I'd say this picture is my gift to you. It's not been articulated, I would say, very clearly in the literature to date. Although I think if you read, like Lenny Susskind's papers or like this Hartman Moldesena reference, they have the tension network picture. So like the precursor ideas are visible. Or my paper on circuit complexity, we had a similar kind of picture where there was a chimera part of the circuit and then a linear part that described the interior growth. So these tension network pictures are floating around, but I would say it hasn't been written down very carefully and taken to its extreme yet to see how far we can get.
Thank you.
Brian, question just about the analogy between islands and this picture. So I understand how this phase transition would happen, and I see how this in some sense can be similar to having, let's say, two entanglement wedges and changing the size of those boundary regions until you have a phase transition between the two. And in that sense, I understand from an entanglement wedge point of view, but from point of view of radiation and a black hole, do you need, it seems like those regions are necessarily boundary regions, right? The ones that you call small and large subsystem. In that sense, I guess you can include as part of the boundary the radiation in a bath, but can you have any notion of this type if the radiation is actually just gravitating radiation far away from the black hole or something like that?
I don't know. I mean, I would answer that by saying I think there's a lot of ingredients missing from this very simple-minded picture, and it would be interesting to add those ingredients in. like to really put an extra radiation region or try to, yeah, anyways. So I have not done that or thought about that very carefully, but I think that should be something, that would be something one wants to do to make this analogy more precise. And, what you consider a gravitating region or a non-gravitating region is not clear to me, but yeah. So I don't have it. I don't really know. Let's just say I don't know. It's a good question.
Other questions?
So in this measurement-induced phase transition model, if you did think that this was a model of ADS-CFT, like, I guess what is the physical interpretation you would assign to these random measurements?
Oh yeah, this has nothing so far to do with ADS-CFT. It's just saying that the goal of this was not to model some existing phenomenon, but to say there's a new phenomenon where you can take a circuit and you can add random measurements. And first of all, the volume law phase is stable, which may be already somewhat surprising, because if you think about like entropy grows like an area, but measurements which are extensive in the bulk of the circuit would naively reduce entropy by a volume law amount. So it seems naively like you would have a steady state which was area law like, but that's actually not true. And the reason why it's not true is because, as we saw here, small size regions actually don't have access to much of the circuit. So you can measure them and project them out and not do that much damage to the entanglement, because the entanglement is actually encoded in these very complex many body degrees of freedom. So there's an important insight about why this highly entangled phase is possible at all, which comes from the fact that these scrambled states sort of encode information very non-locally and form a kind of code, right? And then the high probability where you're measuring very rapidly, that's kind of, I would say, physically obvious. Nothing's ever really obvious, I would say, but it's more obvious, more clear. And so there's a non-trivial insight about the existence of the volume law phase, and then there's and then once you have that, then you sort of know there has to be some kind of interesting phase transition. It could be first order, but we know models where it's actually second order. And then you have some kind of very exotic, in principle, dynamical phase transition at infinite temperature. It's quite interesting, right? So maybe there's some non-unitary conformal field theory that's relevant here, or maybe like you break Lorentz invariance. There's a lot of cool sort of critical phenomena questions. So that's the spirit of the endeavor so far, I would say.
So has anyone like actually mapped this to an error correcting code, or?
Yeah, so one of the main tools in this field is Clifford dynamics. So this is, I didn't talk about this, but this is, maybe this is a class of unitaries where you can efficiently classically compute the result, but nevertheless, you can generate a lot of entanglement. It's of a sort of simple type, but you can still generate a lot of it. And yeah, so in this case, it's sort of known explicitly that you generate stabilizer codes of a certain type. And people are exploiting the properties of those codes. They may even be practically interesting. In the more general non-Clifford case, we think you generate codes as well. And we have some evidence. In fact, I wrote a paper about this with some colleagues, Xiaokai Jian, one of my postdocs, which appeared just last night. So take a look at that if you want. So we still think they form codes, but they're approximate codes and more complicated, harder to understand, because you don't have this nice Clifford structure. But yeah, the codes are there.
Thank you.
Other questions? Okay, so that's a good place to end the recorded part. So